Okay, looking at the final exam review, we're going to take it each bit by bit. And luckily for us, when IB is putting together one of their tests and they have one big question with A, B, C, D, E, F, G, however many go below it, it all builds on one another. So it's basically breaking down a problem that they could make very difficult into a few basic steps. And then you can get the final answer that they could have just asked for initially. And so we want to look at each of these and identify what we have, identify what they're asking for, and by the end should get the correct answer. So we have a couple of bits of information. We have a 0.265 gram sample that's a mixture. So normally we deal with things that are not already mixtures, but this one is, and it's with calcium chloride, which they give us a symbol for already, and potassium nitrate, which they also give us a symbol for. And we know if we're doing balanced equations or anything with the masses of things, we need to know that symbol. So it's lucky for us that they gave it to us already. If they hadn't given it to us, we could just look at the periodic table and figure out what the charges are and then do the crisscross rule. So for instance, calcium is in the second column. It's an alkaline earth metal, so it's a 2+. Chlorine is a halogen, it's a 1 negative. So when I crisscross it, I forget about the charges and I'm left with CaCl2. I need 2 chlorines for every 1 calcium to get a net charge of 0. So I would have 2 times a -1, that's a -2, plus a 2, that's 0. So overall, remember the oxidation numbers of compounds must be 0, which is why our crisscross rule works. The potassium nitrate has a polyatomic ion and an alkali metal. Potassiums are alkali metal with a 1+ charge. Nitrate is a polyatomic, which means a group of elements bonded together that overall have a net charge and can bond with something else. And the charge of nitrate is a 1 negative. So when I crisscross that, it's a nice easy one, KNO3. Remember, when we have ones or when we have the same number, we don't have to write those numbers down to save some time. And that entire mixture is dissolved in 50.0 centimeters cubed of water. Then we do some titration. So when we see that we're doing titration, we're probably going to be thinking about M1 V1 is equal to M2 V2. Or we could say C1 V1 is equal to C2 V2. It depends on what book you're looking at. The M here or the C both stand for the concentration or molarity, and that would be in moles over liters or moles over decimeters cubed. And the volume might not be in the right units for us, but it's going to be volumes of our first is equal to our second, assuming that we have a mole to mole ratio of 1:1. So when we do titrate it, we can titrate it with 0.1 moles over decimeters cubed of silver acetate. Again, it's giving us or silver nitrate, it's giving us the symbols already, which makes life easier, but we could just as easily figure it out the way that we did with these, which reacts with the chlorine ions. So notice we're only reacting with the CaCl2. So even though I have a mixture of stuff, I'm only reacting with the calcium chloride in the form of silver chloride is one of our products. And we need 38.5 centimeters cubed of the silver nitrate. So that would be our V of, we could say the 2 that we need, 38.5 centimeters cubed. The first thing, again, it's taking us step by step. First thing that we need to do is write the equation for the reaction between the calcium chloride and the silver nitrate. I just have to start writing out calcium chloride, CaCl2, again they gave us a symbol up here, is reacting with the silver nitrate, AgNO3. And that, they said, is giving us 2 products. It's giving us silver chloride, AgCl, and it's going to give us this leftover stuff which it didn't tell us about, but it'd be calcium nitrate. And I want to make sure that I get the symbol right because then I can balance it correctly. If I don't get the symbol right, it's not going to balance correctly. So I said up top that calcium is a 2+ charge. It's an alkaline earth metal. I also said that nitrate is a polyatomic that has a charge of 1 negative. So that means when I crisscross, this entire group of NO3 gets that 2 charge. I need 2 of those NO3 groups to be able to cancel out, give me an oxidation number of 0 overall. So I get Ca parentheses NO3 parentheses 2. As you can see, we're not balanced yet. I have the correct number of calciums. I have an incorrect number of chlorines. I have 2 here. I only have 1 on my product side, so I need to put a 2 as my coefficient. And now I have 2 moles of silver chloride for 1 mole of calcium chloride. I can continue looking on. I have 1 mole of silver, but I have 2 moles of silver on my product side. So I'm going to put a 2 in front of my silver nitrate. I now have 2 moles of silver on each side. I also have 2 moles of nitrate, which is good because I have 2 moles of nitrate with this 2 coefficient. So that is my balanced reaction. CaCl2 plus 2AgNO3 forms 2AgCl plus CaNO3 2. This next part asks me to calculate the amount in moles of silver nitrate used in the reaction. That comes from this reaction over here. And I said I was going to use for silver nitrate the 2's. So I'm going to have concentration times volume is equal to the number of moles that I have in a solution. And I have both of those values, except for one little hinky thing. I have centimeters cubed, but I have moles per decimeters cubed. So that means I need to convert centimeters cubed to decimeters cubed. So in 38.5 centimeters cubed, I'm going to multiply by 1 decimeter cubed divided by 1,000 centimeters cubed, because that's my conversion factor, and every 1 decimeters cubed, there's 1,000 centimeters cubed. My centimeters cubed cancel out because 1 is on top, 1 is on the bottom, and I'm left with a unit of decimeters cubed because it's on the top. And I have to move my decimal point over 3 times if I'm dividing by 1,000. So I have a new decimal point right there, and I'm going to fill in a 0 in my missing spot. So I have 0.0385 decimeters cubed as my volume used in my titration. I can now take that, multiply it by my concentration to get my moles. So moles of AgCl, AgNO3 is equal to 0.0385 decimeters cubed multiplied by 0.100 moles over decimeters cubed. Before I actually calculate this out, I want to look at my number of significant digits that I have. So, if I look here, neither of these zeros are important. They don't matter for our number of significant digits. The numbers here on after do. So I have 3 sig figs in my volume. This one, the 0 before the decimal, is not important, so I can ignore that. The 1, 0, 0, all 3 of those are important. When I multiply, I'm looking just for number of significant figures, total, the lowest one, and they're both 3. So my final answer needs to have 3 significant figures. And when I multiply this entire thing through and put it into scientific notation, because it's easier for me to see and write out, I get 3.85 times 10 to the negative 3. And my units, also very important, decimeters cubed have canceled out, and I am left with moles, which is good because that's what I wanted. The next part says I need to calculate the amount in moles of calcium chloride titrated by the mass of the calcium chloride present in the original sample. So I know that my reaction is only occurring with the calcium chloride. I said that in the last step. So it's only occurring with that. It's not occurring at all with the potassium nitrate. Those are just spectator ions. So I'm going to use my C1V1, is equal to C2V2 to solve this problem. I already have calculated my moles that I used to titrate the solution. And I figured that out with the last one is equal to 3.85 times 10 to the negative 3 moles. I also figured out in the last problem that moles of the one is not directly related to moles. It's not a one-to-one relationship. What I do know is that for every 1 mole of, let's go back, the calcium chloride, for every 1 mole of calcium chloride, there are 2 moles of silver nitrate used in the titration. So for every, this is moles of the nitrate, AgNO3, and for every 2 moles of AgNO3, there is 1 mole of calcium chloride. So I have to take 3.85 times 10 to the negative 3 and divide it by 2. And that should give me the number in moles of calcium chloride titrated within the sample. And from that I should get right around 1.92 times 10 to the negative 3 moles. And again, that is of the calcium chloride. It's also asking for the mass of the calcium chloride in that original sample. I know moles now, so I just need to look at the periodic table for the mass of calcium chloride. So I look at the mass of calcium. 1 calcium is right around 40, and I have 2 chlorines right around 35.45, and I get a total mass right around 110, 111. Let's say 110.98, and that's grams per mole of calcium chloride from the periodic table. So now I can convert this. If I have 1.92 times 10 to the negative 3 moles of calcium chloride, and then I multiply that, for every 1 mole of calcium chloride, there are 110.98 grams of CaCl2. I would take 1.92 times 10 to the negative 3 and multiply that by 110.98, and I get 0.214 grams of calcium chloride. The final problem, so let's give ourselves a check. The final problem here is saying calculate the percentage of calcium chloride in the original sample. I now know the mass of calcium chloride that I had, and I know that I started out with 0.265 grams. So 0.265 grams total can go on the bottom. And on the top, we'll go how much calcium chloride I have, 0.214 grams. And since I'm looking for a percentage, I'm going to multiply this by 100. And I get a percentage of 80.7. So of my mixture, approximately 80% of it was calcium chloride.